nanohub.org.
Online simulation and more for nanotechnology.
Hi everyone. So today I'm going to be talking about bridging the gap between large and small using thermodynamics and nanoengineering for the water, energy, and food nexus. And one of the key takeaways here is in the nano facilities, we often only focus on the small, nano-sized things. But if we really want to make a large-scale impact, we need to actually cover the breadth of different size scales. So when we say the water, food, energy nexus, what do we mean? Well, essentially, the major inputs and outputs from each of water, energy, and food are one another. Now, what does this look like? So visually, we have a mix of very small-scale phenomena, membrane design, pathogens, nanofabrication, condensing. We also have very large-scale systems, so power plants, desal plants, environmental flows, agriculture. So to bridge these very different size scales, we need nanoengineering for the small stuff, but we need thermal fluids to bridge the gap. So in my lab, we work on a variety of different techniques that actually span thermo all the way to nano here in purple. And if you're bored during this talk, you can play the game of every single one of these comes up in this talk, so you can look out for those. Everywhere from process optimization from the thermodynamic side, all the way to self-assembly and nanoengineering and everything in between. And so these techniques are very relevant across a wide range of these size scales and actually tie them together. So in my lab, we kind of have three main focus areas with heavy overlap. So we have membrane nanomaterials, we have thermal or other desalination or other thermal transport processes, and thermodynamics for time varying processes. And I'm going to be giving an example of each one of these to illustrate how these tie together. And more globally, you can see there's kind of a mix of many different things from energy efficiency to membrane fabrication, process design, energy storage, etc. So there's going to be three pieces as examples. There's going to be reactive membranes, thermally powered desalination, and electrically powered water treatment. And these examples here will be through isoporous membranes for photocatalysis, membrane distillation as a thermal process, and batch reverse osmosis as a very efficient mechanical process. So we're starting with membrane distillation. So why membrane distillation? What is it? So the advantages of membrane distillation are it's very efficient and it scales down to very small sizes very well. It also has extremely high rejection. You can create ultra pure water with this technology, much more pure than you would have for a traditional water treatment plant. And it's very fouling resistant. And a bunch of companies are currently pursuing the technology. So what does membrane distillation look like? Well, essentially, imagine a heat exchanger, but you just threw a membrane in the middle. So you have heat coming in, top heater up here, and water flowing on the opposite side. It would look like a regular heat exchanger, but there's a membrane here, I showed in orange, and then there is a water-filled or air-filled gap where you're collecting the pure water. And so the temperature difference across this heat exchanger is actually acting to desalinate. And conventionally, people have only looked at fully flooded gaps between the membrane and the condensing surface, or they've looked at kind of film-wise condensation, and I've been the first to look at some of these other condensation regimes and how they can improve the efficiency. So to model these systems, you have simultaneous heat and mass transport processes. So what you do is you take a little slice of that long membrane heat exchanger and you compute all the boundary layers, the thermal boundary layers, the concentration boundary layers, and then you make a few hundred of these elements all lined up where you balance you conserve heat and mass between each little element, and that's how you can model a large-scale system. So we've been fabricating a variety of nano-engineered condensing surfaces to improve the performance. One of these is shown here to create these blade-like structures which give you extremely high roughness and thus can give you really high contact angles, like 172 degrees. As a result, you can get jumping droplet condensation, which can give you really enhanced mass transfer coefficients. We're also looking at other types of enhancement, such as rapid draining through hydrophilic and channels and other hydrophobic areas, with a goal of trying to decrease the overall gap size. So if you want to look at what of these cool condensing regimes look like. One of our collaborators is Professor Nenad Miljakovic. Watch these two droplets over here. So they merge together and then they jump off the surface. And if you zoom out, you can see them hopping all over the place. You can imagine your mass transfer coefficients are pretty good here. So why are they hopping? Essentially, you have two droplets and they're growing. Once they touch, they merge, and that surface area reduces dramatically. That surface energy has to go somewhere, and so it goes to wobbling. And they're so poorly adhered from the surface that the wobbling makes them eject from the surface. And this can give us high mass transfer coefficients. So an ideal surface has a few properties. It has high roughness for enhancing the hydrophobicity. It has a low surface energy coating for the hydrophobicity. It has a thin self-limiting layer for the coating because you don't want to create a large thermal resistance. And you want a very highly thermally conductive coating. In this case, copper oxide is maybe a quarter of the thermal conductivity of copper. So it's still performing very well. And it's got to be robust and it's got to be cheap. We're also looking at some other novel applications, the first slip surfaces for these applications, so lubricant impregnated surfaces, as well as channel designs that are going to help really rapidly drain these channels. So to visualize these systems, this is an older apparatus, but we condensed on a sapphire condensing plate. So it took many, many months. I think it was 9 in total to acquire the sapphire plate. Sapphire, because it has a really nice crystalline structure, has a really high thermal conductivity because vibrations, aka phonons, that are transporting heat can move very rapidly. So it's on the order of 32 watts per meters Kelvin, which is about 100 times that of a plastic material. So this we can use as a condensing surface and visualize things in ways that haven't been able to be done before in desalination. And so we can see a few different regimes. We look at spacer designs, as well as these jumping droplet surfaces, and we have more results to come with our brand new apparatus we have. Some of the takeaways when we go to jumping droplet condensation, we have an increase of the overall flux. So especially at lower delta T's, which are more realistic, we can even double our permeate production rate. Our total cost can be represented on a flux versus an energy efficiency called Gore curve. So we're dramatically moving up this curve, this whole frontier, by having these enhanced surfaces. And you can think of the flux as kind of a membrane area, so that's like a capital cost, and your energy is largely your OPEX. And these two costs dominate. So enhancing the transport in these systems can dramatically improve the competitiveness of the technology. So where is this most useful? We can improve the energy efficiency. Can we do this in other thermal technologies? Quite possibly. Thermal desalination is maybe a third of all desalination available. Also, can we use directional wicking to improve performance? And how do we design the nanoengineering surfaces differently if we have a full-scale system and process design in mind? So next, I'm going to be talking about another technology. This is batch reverse osmosis, which is an enhancement on the regular reverse osmosis. So if we look at the desalination capacity map, reverse osmosis is the majority of processes. The thermal processes shown in orange and red are also important, but not as large in terms of total capacity. Over time, the energy needs for seawater reverse osmosis have gotten very low, and so they're much lower than the thermal technologies. So there's a niche where reverse osmosis is most competitive, which is an extremely viable technology. And you can see there's been a steady march down of the energy needs for seawater reverse osmosis, or SWRO. But it's still at least a third of the cost, so we still want to bring this down even further. Now, the top challenges for desalination processes are the energy efficiency as well as membrane fouling. And we're going to address both of these with a batch process. So reverse osmosis is the technology most in desalination that most people are familiar with. You have a high pressure pump, you have a salty feed, and you apply enough pressure to overcome the osmotic pressure. As a result, water will go from the salty side to the less salty side, and you're essentially doing PDV work in this process. What this looks like in reality is we take this long membrane channel, and then we wind it up into many dozens of layers, which give us extremely high surface area. And then we put many of these elements in a row to have a massive desalination plant. These plants can be huge. They can be the size of multiple college gymnasiums just filled with these things, supplying the water. Let's say about a third of the municipal water of San Diego is provided by a plant using these membranes. In Israel and the Middle East, they use very, very large, even larger plants, almost 3 times larger than the San Diego plant, to provide large amounts of water. So we're talking about using a batch process to enhance the performance here. So what is a batch process? Well, in chemistry and engineering, etc., we always think of batch as we have a set volume of some liquid, and we do something to it in one step over a time step, and then we repeat the process. So it's kind of a cyclical process. And often people try to move towards a continuous process when they think of scaling up, but really you can do a batch process at very large scale with the proper design. So in the batch process I've proposed here, we're talking about cycling the salinity over time and cycling the pressure that's applied over time. And this gives us a lower pressure in many stages than the overall pressure a standard desalination process would have. So if we want to look at what a standard reverse osmosis desalination process and how it operates, we have some applied pressure, and the pressure in the module kind of goes along this top curve here. And this is the fraction desalinated. For those who know the jargon, this is the recovery ratio in desalination. And it so happens that because this is PDV work, the areas here actually all represent energy. So the green area here represents the least work for separation. It's a penalty you have to pay by thermodynamics. But a traditional process has all this extra energy because you're needing to apply enough pressure to overcome the final osmotic pressure and to deal with your friction losses. So the idea of this batch process is to bring this whole curve down by cycling the pressure over time, kind of following the osmotic pressure while dealing with these two. So this graph will become more like this, and an entire region that's gone here is going to be your batch energy savings. So how do we model a process like this? And this comes into where the thermodynamic design comes into the smaller scale. So again, we use a discretized element where we take our long membrane module and break it into many different slices. And here we have to balance, we have concentration profiles shown in red. We have a membrane active layer, which is often a source of nanoengineering, which I will talk about soon. And we have to balance the mass flow rates of not only water, but salt between every element that we add up. And we have to deal with the fact that these membranes aren't perfectly rejecting. They don't reject quite as well as the first process, membrane distillation. So you're having some salt permeate through the membrane. And so you actually have to incorporate and understand the transport that is occurring within the active layer and within the module itself. So what does a traditional reverse osmosis desalination process look like? Well, essentially you have an incoming feed that's salty, you have a high pressure pump, and then you have a bunch of modules chained together, and each one is producing more and more pure water. And typically, in many cases, especially at seawater or higher salinities, you put some type of energy recovery turbine or other device on the brine exit here, because this brine is leaving at high pressure, and that will be a large loss to your system if you do not recover that energy. So a batch process kind of changes the configuration. Instead of having a continuous flow, we have some variable volume high pressure tank that applies a pressure over time to desalinate. And so over the course of a cycle, the pressure would ramp up and the circulation would continue through here. And we want to do this process in a way that the tank storage is both controlling the volume and pressure simultaneously without any energy losses inherent to that storage. That is a difficult thing to do, and it's why it hasn't existed in the past. And it's a difficult thing to do to be able to control the pressure and volume simultaneously. And so previous systems have looked at semi-batch processes and have not made a true batch system that can cycle the pressure to save energy. So it's efficient, but how do we make a tank that does this? How can a tank change its pressure and volume simultaneously reversibly? So can we use a motor? No, we have motor losses. Can we use springs? No, we don't have the pressure over time control. What we can do is we can actually start filling the void space of the tank in a clever way. So we take our main high pressure pump and we move it to fill the void space of this tank with the permeate. and then we add a little circulation pump and run a cycle like this. So this pure water is displacing this piston, and this actually is very efficient in a few non-intuitive ways. So here we have a closed system instead of an open system. So in the batch process, we had a very large volumetric flow rate of brine that was leaving the system, and that had a very large energy loss associated with it. So we needed to have expensive turbines to recover that energy. However, in a closed system, if you had a volume of incompressible fluid, which is water, essentially incompressible, you compressed it really high, and then you depressurized it, right? Your PDV work, when dV is essentially zero, approaches zero. So you have nearly no energy losses when you depressurize this system. So you can do this without actually needing these high pressure energy recovery devices. And at the end of each cycle, you have to refill and repeat. We've actually looked at a few different iterations of this design with different fluids in this system, but we need to file the patents before we can disclose all of that publicly. In analyzing these systems, again, we break them up in these discretized models, and we can actually model the salinity gradients across the length of the model over time. So these are quite sophisticated simultaneous heat and mass transport processes. So here are some results. I want to thank Sandra for doing this hard work, and Abim and you as well. And so we can look at the energy needs on this scale of batch RO compared to the continuous with pressure recovery, which is kind of the state of the art now in these large desal plants, and then the older technology, or what was typically used at lower salinities, which is continuous RO without an energy recovery device. And you can see here very simply, this is all these blue colors, you know, in the range of almost often below 2 kilowatts hours per meters cubed, where the other technologies need a lot more energy. If we want to directly compare these two back to back, we can look at the energy improvement of the batch RO system compared to the main state-of-the-art process. And for some context, seawater desal plants are typically operating over here in this range, so we're looking at a low 20% improvement. And groundwater and water reuse use very high recovery, so they're operating up here. And in fact, those groundwater systems tend not to use these very expensive recovery devices, so we'd actually be comparing to the even worse technology and have an even more superior energy result. There are some other nice advantages of doing this. So we're cycling the salinity over time. So instead of having the end of our module always be really, really salty, maybe twice the salinity of seawater, which could be about 7% salt by weight, we're cycling the salinity, which means our residence time of it being salty is very short compared to a continuous process. If the nucleation induction time, which is essentially the time it takes for crystals to begin accumulating and causing large-scale crystal growth, there's a delay time because of the competition between surface energy and the volumetric terms. Essentially, to create a new small crystal, you need to build a lot more surface energy, which is unfavorable. But even when volumetrically, if you're super saturated, there's a volumetric term saying you want crystals. So you have a delay and then runaway growth. If you operate quickly in these cycles, you can stay below this time and you can go to much higher recoveries. So what this looks like, if we can use models that we have for calcium sulfate and calcium carbonate, we can actually map out the residence times versus the anticipated large-scale nucleation events. And we see for a batch process, if we have, let's say, a source that comes in at 50% of the saturation concentration, the batch process for calcium sulfate could get to upper 80s or 90% recovery, whereas a continuous process is going to fare much worse and maybe only be in the upper 70s. So we can get much higher concentration, which means we can take our most efficient process and extend the salinity ranges it's viable for. If we want to compare this on various source waters, we took a USGS database with literally hundreds of thousands of data points, enough that the Excel was crashing my computer just because it took so much RAM, which is kind of a hard thing to pull off. And we can look at the average, we can get representative average groundwater, and whichever one of these is lowest is what's limiting your recovery. So for seawater with a batch process, we can get to maybe 76% recovery, whereas for continuous processes that are all locked in, at maybe 60% recovery because of the calcium sulfate. This is actually a fairly big deal because they're taking these huge volumes from the ocean for these plants, and they're often doing intakes, like in California, that are many miles off sea, enough that it really drives up the cost of desalination, just so they're not having an environmental disruption of that intake. And then they have to do pre-treatment on all this water, which is going to use chemical inputs and a lot of pumping energy. And so by also reducing the amount of water that you have to you need to intake for the same pure water produced, you can reduce the costs, the chemical consumption, and other types of energy use that are not captured in the results I've shown so far. And we can also see that for groundwater and for extreme salinity groundwater, we do a lot better with the batch process compared to the continuous process. So where can we use a process like this? Well, it actually covers a very wide range of applications. These large-scale desal plants, like the Carlsbad plant in California, that serves San Diego. Also, we get much higher energy efficiency for these low salinity applications. So it's great for agricultural water use and water reuse. So recovering agricultural water, reducing the salinity content, which we can reduce the salinization of fields. This is a major global issue, not only because of agricultural practices, but also because of, let's say, road salts. And in fact, the salinization of arable land is such a major issue that it has actually ended multiple civilizations, right? The first example most people are familiar with is the civilization of Mesopotamia. They tried to switch to using saltier and saltier tolerant crops because their water practices were having water evaporate, adding new water, leaves behind the salt, and having it evaporates. So the salinity kept increasing. And eventually they couldn't have crops that could grow on their land, and their agricultural land dramatically decreased, and it led to a major decline in that civilization, which is why they're not the global power today, and instead kind of a crisis. And if you look at this Syria conflicts that's happening there, a lot of that war was instigated by a multi-year drought. So these water issues are actually very major in causing interstate conflicts. We can also look at household disinfection for these systems. So a major problem in places like India is the water is not safe to drink. What's essentially happening there is not only are the treatment practices imperfect, but their infrastructure is fairly leaky. So in the U.S., we are maybe losing 15 to 35% of our water in leaky pipes, which is lousy but tolerable. In more developing places, it can often be more than 2/3 of their water being lost. So what they do to conserve water is they shut off their water systems at night and during low demand periods. That saves lots of water, but if you have a depressurized pipe, you shut off the water, you shut off the pressure, other water from outside can infiltrate, right? They have toxics in the environment, they have problems with open defecation, they have untreated sewage water, which is a major problem in much of the developing water. They don't treat all their sewage. And even in our developed cities with older infrastructures, like New York City and Boston have combined sewage and water systems. So we're actually dumping sewage water into the main rivers when you have a big rainfall event. And so you get really large-scale contamination. Globally, waterborne disease contributes to about 3 million deaths per year. So it is a very substantial issue that is far more than are dying from war. And the only things that's a preventable cause of death that really exceeds it is famine. It can also be used for mining water treatment because we're extending the range for the salinities that can be tolerated here. Now, one thing I meant to mention with the household disinfection, these typical systems, while they make water safe to drink, they actually have very low recovery ratios because they don't have any internal cycling. So they only recover maybe a quarter of the water, or usually less, because they have such small memory area. This is a kitchen cabinet in a kitchen. And as a result, they're sending most of that tap water back into the sewage. So they're actually reducing the net water available to the region. But if you had a batch process that's a miniaturized one, you can get high recovery at high efficiency, and thus you're effectively increasing water supply. So we looked at a batch process and how the thermodynamics can improve the performance. How can nanomaterials further enhance the system? So if we want to look at the module, and then we want to look even closer at the membranes themselves, we can look at using ultra-permeable membranes to enhance the performance. So one of my students is looking at modeling for graphene membranes and also carbon nanotube based membranes for not only desalination but enhancing sensors. These membranes can have dramatically higher permeability. We're talking orders of magnitude. So now if you want to look at the efficiency versus the permeability, typical membranes are between 1 and 2 LMH per bar, which is a metric for permeability. And with enhanced efficiency, we're driving down the curve of performance, so we're reducing the energy needs. And these improvements are decent, but they're actually less than we can see for enhanced process design. And so while most of the nanofield is only concentrating on cool materials, we really do need to consider thermodynamics if we want to properly address these issues. And finally, for these systems, I want to look at costs. So with these batch systems and ultra-permeable batch or UBRO systems, we're dramatically improving the cost from RO or versus MED or multi-effect distillation, which is the cheapest thermal desalination technology. And we can find that the batch RO process is predicted to be the most cost-effective of the different possible system configurations. We're looking to implement these systems at a larger scale on microgrids in regions of the world where there's actually a heavy, not only waterborne disease burden, but also a heavy metal poisoning type burden. So we're looking at these water energy microgrids that are using these batch RO systems. So this is one of our microgrids. We're collaborating with Luciano Castillo's group on wind and solar panels, RO modules. These systems on the microscale side are around 10 meters cubed per day. Whereas in our lab, we have systems that are as small as a few milliliters per day. So it's a lot of different orders of magnitude that we're spanning. And we recently did a study abroad in Peru collecting water samples to study the heavy metal contamination throughout the country, which is a major issue because of all the mining activities. So Peru actually is often rated as having the worst water problems in Latin America, and that's why we're heavily involved there. Finally, I'm going to get into looking at some of these reactive membranes and specifically looking at an example here of isoporous membranes for photocatalysis. So we're making these inverse opal fabricated membranes, and essentially these are membranes that we self-assemble a large number of spheres that are going to be sacrificial. Once we remove those spheres, we're left with a porous structure which we want to use as a membrane and a photonic crystal. And the self-assembly process that we're using is actually self-assembly at a meniscus where the evaporation essentially pulls these together in a lattice. And so in terms of applications, we're looking at photonic crystals for photocatalysis. We're looking at plasmonic effects to make it enhanced membrane solar absorbers. We're looking at size selectivity to improve sensors. We're collaborating with Jackie Linnes's group on cholera and HIV sensors. The really consistent pores you see here are very good for trapping molecules of extremely specific sizes. And we also are looking into biosensors with these systems. On the photocatalysis side, membrane photocatalysis can be a very promising technology to address these growing emerging contaminants. Think of not only chlorination byproducts, but all these things we have like estrogen mimicking compounds, pesticides, and other things we're introducing into our waterways that we need to break down. The problem is the existing membranes have enough poor performance issues that they've actually failed to make it into industry. One is there's poor penetration of UV light into typical reactors. There's basically one layer of membrane. The membranes available actually just absorb most of the light, and actually most polymeric membranes will be destroyed by either UV light or the photocatalysis itself. So we're actually making glass-type membranes that are TiO2, SiO2 hybrids that are very robust and durable because they don't have these vulnerable carbon-hydrogen bonds. And we're looking at increased packing density. The photocatalysis? Yeah, so great question. So essentially, UV light comes in the titanium oxide case, it excites an electron, which kicks off the surface and creates a hydroxyl radical or an OH radical that wants to dump its electron, and so it's extremely reactive. And it'll basically, any hydrocarbon it can find, it'll react with and break the bond, and they're really, really great for degradation, but they also disappear very, very easily. So you need to have extremely high active area for the process to work. So we've kind of shown an example here. UV light coming in, it's kicking off this radical, it's breaking down the bacteria, viruses, organic pollutants, and only pure water comes out. So because we have these structures that are extremely consistent, we can actually make photonic crystals that are also membranes. So what is a photonic crystal? Well, the examples we've seen are like, if you have any really cool fossils, like I collect fossils, often you can get opalized fossils. Essentially, you have small colloidal particles of similar sizes that form and fill the gaps of a fossil, which gives you this kaleidoscope of colors. And the varying size of those small particles that have formed gives you the varying orange to green colors. And so these structures are similar in size, but usually a fraction smaller than the relevant wavelengths of light that we can see visibly with them. Peacock feathers, bird feathers, and LEDs is the main area where this has been commercialized. What we're looking at is using band gaps that can have slow photon effects, basically slow light down in the photocatalytic range to increase its absorption by the photocatalysis, and thus essentially be able to create more hydroxyl radicals for the same unit energy input. So when we self-assemble, the membranes kind of look like a bunch of small particles. We're doing a lot of 280 to nanometer size, right? So this is similar in size to relevant wavelengths of light. And then when you remove them, they kind of form a structure like this. And we're making these out of a variety of materials. So we're doing TiO2, SiO2, copper, and nickel. And here's one of our copper membranes here, which we're also using to enhance transport for heat exchanger type multi-phase flow scenarios. Question?
What's the scalability of the meniscus method to form these crystals?
That's a great question. So it's more scalable than most nanofabrication techniques. So if we want to compare it towards etching type techniques, those tend to be very fundamentally expensive because you need a mask and everything. Ideally, this would eventually go to a roll-to-roll manufacturing process. So it is thought as for pores that are 1,000th the size of the human hair, probably about as one of the most scalable processes, but it's still in its early stage. It has not been commercialized yet with the self-assembly technique. But in theory, sacrificial spheres that self-assemble themselves, so you don't need to have expensive etching equipment to make every pore, is very scalable compared to the alternative processes. So one major challenge that we have in these systems is cracking. So we developed a crack filling technique in our group where we're using an electrode to make anodized aluminum oxide to fill the cracks in these membranes and also make AAO or anodized aluminum oxide type membranes. And essentially, you have the opal here and you have the anodized aluminum here, and you can see that the cracks have been fairly well filled with a smaller pore size. We're still working on this, but it's an exciting way because it's the first porous crack filling method for inverse opal type membranes. And essentially what's happening is when this anodizes, it actually grows vertically out of the substrate, and this growth plugs the cracks. And then we remove the opal spheres, and then we have a porous membrane. In terms of flow design, here's one of our cross-flow reactors for testing membrane photocatalysis and these small-scale systems. You can see it's a bit smaller than our water energy test bed. Active area here is like a square centimeter. And what's happening in these systems is essentially the UV light is slowing down and often getting multiple reflections as it produces these radicals. And this structure can allow us to have isoporous selectivity so we can have enhanced catalysis for certain sizes. We're also looking at sensors. So if you look at it statistically, if you have a specific pore opening size between these cells, we can have molecule trapping for very specific sized things. So this is something we're trying to look at for viruses and bacteria detection, because we can size them to trap the very specific sizes of those viruses or bacteria. And actually, the pore sizes are very well aligned to cover even the small viruses. So finally, kind of in summary, with the Water Food Energy Nexus, we have a bunch of different projects that fit into this nexus. So we can have membrane distillation, which is water energy. We can have membrane design, including hydrophobic membranes. Batch processes that enhance performance. I haven't mentioned this, but I've also been involved in a startup called, I'm co-founder of a startup called Coolify, looking at refrigeration with phase change energy storage. In the nexus of all of these, we can look at in nanofiltration that is tailored for crops, as well as groundwater extraction and energetics, so providing groundwater for crops that has to be treated because it's high salinity. I'm also been looking at disinfection. One of the problems I've been hitting my head against a wall with for a very long time is how can we use the evaporation of the surface itself to power disinfection, so we can have a kind of silver bullet type device that can disinfect anywhere. The thermoelectrics were unsuccessful because they were second law efficiency at low delta T's become zero. We recently did a Stirling engine cycle, and essentially to make that really work, we had to start adding warm water or near boiling water, and we can get very good ratios. Like it could disinfect with 1/8 the energy it would take to just boil the water. But we're still not there yet on disinfection, but it's an active area of interest. Nanofiltration for food, graphene membrane type fabrication, and also carbon nanomaterials for enhancing sensors and membrane performance. And membranes for other applications such as HVAC applications. And doing some work on commercializing not just all the science. And so with thermal energy and thermofluids and nanoengineering, there's different nexes of thermodynamic system designs, transport enhancement, membrane nanomaterials, studying membrane fouling, having selective solute removal, and integration with renewables, which are all things I'm working on. And areas for collaboration are shown here, which include wind energy, solar, and other types of research groups on the material side and the transport side, and specific technologies to enhance performance. And hopefully we'll have some more startups and IP licensing in the future. We currently have a wave of patents we're trying to get submitted. Finally, I wanted to thank my team at Purdue. A lot of this work was also done in my past work from my postdoc and PhD at MIT and my joint postdoc at Yale. And thank you. Questions?
I have a question. How do you define efficiency for water systems? I mean, is it energy output divided by the energy input? So what is the definition of the efficiency?
Yes, so it's a great question. For desalination process, it's very easy. There's a minimum least work to separate salt out of a salty solution, and it varies by a given recovery ratio. So if we looked at the earlier slides in batch reverse osmosis, where we had salinity on one axis and we had a recovery on the other axis, there's a direct relationship between those two in terms of a minimum least work that it would take to do that separation. And so we compared the energy we need compared to the least work, which is a function of the salinity inlet coming and the recovery. So for recovery here, and inlet salinity.
And which of these technologies are the best currently? Reverse osmosis is the best technology that we are using nowadays?
Where most desal plants are using this process. So this is like, if you think of these giant plants that are in Carlsbad or in Israel, they use a continuous RO with pressure recovery device. So we're pushing the point that actually the batch systems can outperform them.
There are some other developed methods, technologies for desalination, like capacity realization, electroionization, they're using electrical energy directly. Are your methods better than that methods in terms of using energy and the output?
Yeah, so the most competitive electrically direct method, direct electrical method, is electrodialysis. And that you basically have desalination with a membrane. One membrane lets the positive ions pass, and one membrane lets the negative ions pass. And electric current can make them self-sort. At extremely low salinities, it's easier to make the ions move around than make the water move around. So at very, very low salinities, it can be a very competitive process. Now you saw here this batch RO at lower salinities is doing very well compared to the state of the art. So this is going to push back the region where the electrodialysis system is king. But it kind of has a niche at the very small sizes. It's still a small part of overall capacity, but at the mid, let's say the low to the mid-high salinities, reverse osmosis is kind of the king technology. I will say that there's some technologies which we are having a healthy skepticism to, one of which is capacitive deionization. The problem is it doesn't actually have a separating device, so you can just have back diffusion of your ions into the bulk. For it to really be effective, it needs to have a absorbing material that's selective, and perhaps its potential is in selective technologies. But for general desalination, it's thermodynamically not doing well compared to these technologies.
My other question is the membrane you are developing are just for desalination. You cannot use for elimination of the other biological contaminant or something.
So the inverse Opal membranes are largely for chemical and biological contaminants, and they're pore size. So the desalination membrane pore sizes that are for reverse osmosis are a fraction of 1 nanometer. Whereas our other pore sizes there for these larger scale contaminants like viruses and bacteria are, let's say, 30 to 1,000 nanometers in size. So we're doing a wide range of separations. We're also doing some water vapor from gas separations.
So for complete, you need to use different steps for desalination and the other step for the elimination of the biological contaminant, and for complete purification of water, you cannot combine the methods and have a complete method for doing all together.
Yeah, we can combine the methods. So typically, as you're saying, the reverse osmosis will often need a pretreatment with a larger pore size. We were actually about to do a study showing that the batch reverse osmosis system needs less treatment of biological matter because the cycling salinity should be biocidal. And Sina has been working on that. And we got some membranes from a similar process that wasn't designed for energy efficiency, but was cycling the salinity. And we couldn't get any live bacteria from the membrane. So it's working, the process is almost improved by we couldn't even do our experiment because the membrane that we wanted to show that these membranes that had this type of organisms that could survive there were substantially impaired by salinity cycling. But we couldn't get a damn biological sample off these membranes. So we'll keep trying on that front, but they should need a lot less pretreatment.
All right, well, if there are no further questions, then...
I have one last question. What is the most significant loss in RO process, reverse osmosis process?
Yeah, so I'll pull back up the earlier slide here to kind of maps out the losses. Essentially, a lot of it is almost unnecessary losses. So essentially, you're applying way more pressure than you need to for the given membrane system because of the configuration. You provide enough pressure to exceed the osmotic pressure with some extra pressure for membrane permeability at the exit of the module, where the osmotic pressure has increased dramatically. And so you have a lot of essentially unused energy. And this, if you want to think specifically, it's kind of occurring in the membrane module, but it's because you've provided more pressure than you need for most of the membrane system. One way they improve this is in some systems they can use 2 pumps. So essentially it would start maybe over here, and then they switch to the second pump and it would go up here, and they would remove this whole chunk in this corner by having multi-stage pumping design. But a batch system kind of operates like an infinitely staged with infinite pumps.
Right, okay. And the last question regarding the temperature, the effect of temperature on permeability of membranes that we use in this technology. Do you think that temperature has an effect on that? If we increase the temperature of the entire system,
Yeah.
the heat and mass transfer processes becomes faster. I do understand that there is another energy input that we need to take into account when we calculate the final efficiency. But I was just wondering if there is any effect by.
Sure. So I have a paper with my colleague Yanginaseni Roy on temperature and how it impacts nanofiltration. And essentially, it increases the water flow rate a lot, but it also increases the ability of salts to penetrate through the membrane. So there's a trade-off there, but there's some situations where it could be very favorable to use at higher temperature. And you can also tailor the pore sizes so you can deal with the concerns you have with higher transport rates of certain salts.
All right, well, if there are no further questions, then we should thank our speaker who was kind enough to put this together for us.